progress.
Hi, Jordan.
Hello.
Hi, Jordan. Do you have any questions?
I do. I wrote the number down and I'm trying to find it.
Being organized is the worst thing.
Okay, let me see. There was one question that I know I got confused on. Okay, I have it in here somewhere, I promise.
Okay. Was it in the homework? Was it?
It's from the quiz.
Okay.
It had something to do with chapter 15. It was one of the last few questions it asked. Like if the products were like released or positive or something like that.
Okay.
Out of the PowerPoint.
This is the quiz? The quiz you said?
Yes.
Okay. That's it. Easy enough. I can pull it up.
Okay.
Okay. Let me get out of courses. What am I doing? Okay, there we are. And that was quiz 2 or 3?
3. It's the one that's due today.
It's due at what time?
I think it's due at 10.
10. Okay. Wait till after 10. I'll answer it.
Okay.
Let's just one of the last ones.
Yeah.
Okay. Rate law, what order?
Yes.
Okay, we're going to get into that today.
Okay.
All right.
Yeah.
We will get into that today. It's actually a simple answer.
Okay.
Okay.
Do you want me to wait until 10 to like ask you about it?
Yes,
okay.
Because believe it or not, there are people on here right now and they could get the answer and put in the right answer.
Okay.
Because the quiz hasn't closed yet. Does that make sense to you?
Yes, it does.
Okay. Zachary or Vanessa, do you have anything you need to ask me?
Yeah, I have a question. I'm in your face-to-face lab, and there's the lab safety quiz and the syllabus quiz due today. And I was able to complete the syllabus quiz fine. I'm just confused on the lab safety quiz because there's no lab safety document displayed on Canvas for me to be able to take the quiz. So I'm not sure what information I'm supposed to use in order to take that quiz.
Okay, I gave the lecture last week.
Yes, correct. But isn't there like a safety document that we need with a list of rules? And then that's how we are supposed to take the quiz? Or is this something that is...
Okay, from now on, I'm doing it now, but you can't wait till the last minute to do these things. Yes, I should have put this piece of document up there. Had somebody told me about this, then I could have had it uploaded for you.
I emailed you about it yesterday, Professor.
When did you email me, Zachary?
I emailed you early in the afternoon.
Okay, what did I tell you about when I answer emails?
I'm not sure.
I told you that I answer emails in the morning as a general rule. So if I answer them in the morning, I wouldn't have gotten into it until today. It's in there now.
Will it still be the same due date at 2 o'clock?
No, it will be 5 o'clock tomorrow.
Okay, thank you, Professor.
Anything else, ladies and gentlemen? Vanessa, why are you in here so early? Jana?
Oh, I clicked on the thing you sent and I thought the class was starting.
No, the class starts at 10:15. Okay.
Oh, okay.
What I do is I come in here early for my office hours. Fair enough? Jana, any questions?
Yes, it's just a quick question. I'm in your face-to-face lab, and I just wanted to make sure that there is a class today.
Yes, there is a class, and it will be at HCC. You will be doing a lab. You're going to be doing the heat, the vapor pressure and heat of vaporization lab.
All right.
Literally speaking, Janet, you are going to be in there. The actual experiments to take the measurements is going to take you about a half an hour. That's it.
All right. Sounds
okay.
Good. All righty. I also wanted to ask if I could look over the answers for the quiz, but the one that was due, like, right about
in 1 minute. Yes.
Okay.
The quizzes are the quizzes are due at 10 o'clock, and that's when the answers get published. So if I give you, this is a strange thing, somebody can actually look in there and grab the answers before the quiz gets closed.
Okay.
And
right.
I'm in the wrong class. Be there in a second.
All right.
And I'm sure we're counting down to the last second here. Okay, 10 a.m. We can look at it. Okay, let's see. Jordan. Your question, Jordan.
Yes.
Had to do with the order.
Yeah.
The order of the reaction. Rate laws relate the rate to the concentration. We're going to get into that later on today. Okay? And what the rate laws do is the rate is equal to a constant, the rate constant, times the concentration of your reactant raised to a power. Okay, Jordan? And if I'm talking about the overall reaction order, I have to add the exponents for each one of the reactants that are within the rate law. Does that make sense, Jordan?
Yeah.
So in the rate law, rate is equal to K, concentration raised to the second power. The order is going to be 2.
Because you're adding the exponent?
Yeah, there's only one, the rate is only dependent upon one particular compound, but it's related to that compound's concentration squared.
Okay.
So order is equal to the the addition of all of the exponents in the rate equation. So in this instance, that answer should be 2.
Okay, thank you.
Jana, your question.
I had the same exact question, but can you please repeat it again? I don't think I understand.
Okay, when we get into rate laws, a rate law relates the rate to the concentration of one or more of the reactants. And the concentrations in the rate law can be raised to the second power, or it could be raised as much as the third power. It won't go beyond that. So the order of a chemical reaction is the addition of all the exponents within the rate law. So the rate is equal to the rate constant times the concentration of A raised to the 2 power makes the order of that reaction 2.
Okay, thank you so much. I think
No problem. Anybody have anything else out, guys? If nobody has anything else out, I'm going to go get my glasses. I'll be right back. Okay. No more questions, guys? Nothing?
I'm just gonna look over my quiz to
Okay.
see if I have any other questions.
Well, if you want, I can show it and see what you did wrong, and we can go over that. Would you like that?
Yeah, that would be good.
Again, I have to show it. That means everybody's going to see it. Is that okay with you?
Yeah, I think that's fine.
Okay. Okay. 34.0034% is how many ppm? Okay, Jana, there are a couple ways to do this. The first thing is you can just rely on faith and multiply a percentage by 10,000, and you will get the correct number. Or you can just say, okay, 0.0034 divided by 100 is equal to X over 1 million. So if you do either one of those, you get 0.0034. You get an answer of 34. Okay? Probably a simple math problem.
I think for this question, something went wrong with my calculator because at that point, my, I think I messed like a decimal point or something and I messed it up. I think that's why I ended up with the wrong number.
Okay, this is Raoult's law. And basically you have to use molarity and you have to use molarity and you have to use wait a second. I'm okay. Sorry, my wrong. You have to use mole fraction. The new pressure is equal to the mole fraction of the solvent times the vapor pressure of pure water. So you got to figure out how many moles of sodium nitrate you have and how many moles of water you have. In this instance, what you were doing, moles of sodium nitrate. Sodium nitrate is NaNO3. Sodium weighs 22.99. Nitrogen 14.01, and 3 oxygens are 48. That means the sodium nitrate weighs 85. You take the 17.5 grams of sodium nitrate divided by 85, you get the moles of sodium nitrate. You take the 50 milliliters of water, since it's 1 gram per milliliter, that's 50 grams of water. Divide that by the molecular mass of water of 18.02, you get the moles of water. Mole fraction of water is going to be the moles of water over the moles of water plus sodium nitrate. You multiply that by the 23.8, you get the new pressure. Okay?
Yeah, got it.
Okay. The first part of this question doesn't mean anything. The first part of the question really means nothing. You put salt in water. Does the freezing point go up or does the freezing point go down?
For me, this one kind of confused me a bit because last semester I was kind of doing an experiment, and so when I did some random research, I ended up getting like the salt water solution actually raises that. So I wasn't 100%
I'm sorry,
sure.
Jana, the what water solution? I didn't get that last statement.
The salt water solution actually had like a higher freezing point because like salt
it can't happen. Janet, it can't happen. There was something wrong with your research, okay? Because freezing points get depressed, boiling points get elevated, always. So if you put anything in water, it's going to lower the freezing point. All right, this one. Okay, somebody's got some background, a lot of background noise. Sounds like a family back there.
Oh, fuck. One more, Poppy? Oh, that's the protein drink she told you to order? Yeah, it's all of it, bro.
Somebody has got some background. Everybody put on your...
What the fuck that nigga said?
Manuel, put your video on. Ethan, Araceli.
Class don't start till 10:15.
Manuel.
Oh.
Okay, it's not you.
What do you say?
Somebody has got there's a lot of noise in the background. Okay, thank you for muting yourself. This question, okay, there are 2 factors. We're going to get into the Van Hoff factor today. And that is the more particles. Remember, we're talking colligative properties. Colligative properties deal with particles. Now, you got to look. HCl has 2 particles. It has an H ion and a Cl ion. Glucose doesn't break up into particles. When it gets thrown into solution, the water surrounds the entire glucose molecule. So glucose has 1 particle. Potassium sulfate, 2 potassium ions, 1 sulfate ion. It has 3 particles. Calcium phosphate, 3 calcium ions, 2 phosphate ions. So what happens when you have a concentration of these particular substances? The 6 molar is the molarity of the HCl. But since HCl makes 2 particles, you double the concentration worth of particles. So HCl, 6 molar HCl gives you 12 molar particles. 8 molar glucose, since the glucose doesn't get broken up, gives you 8 particle molarity of glucose. Potassium sulfate, 5 molar, 3 particles, 15. So it is bigger than the 8 from the glucose or the 12 from the HCl. Calcium phosphate, 3 particles calcium, 2 phosphate, 5 times the molarity of 2. The calcium phosphate is less than the potassium sulfate. So potassium sulfate at 5 molarity is the correct answer.
Okay, got it.
And we went over that.
I'm sorry, Professor. I wasn't here for question 9. Can you go over that one more time?
Question 9?
Yeah.
Yes. You should have been able to find out from the scanning of the PowerPoint or the reading of the chapter what an order of a rate law is. A rate law relates the rate to the concentration of the reactants or products, but it just doesn't relate it to it on a one-to-one basis. Sometimes the concentration is raised to a second power, sometimes to a third. When I refer to the order of a reaction, this is the addition of all of the exponents of the concentration of the reactants. So in this case, I've got the rate is equal to a rate constant times the concentration of A quantity squared. Because of that, the order is going to be 2. Okay, Natalie? We are going to go over that today.
Thank you.
Anybody else have any other questions? We're at 10:14 anyway. Okay, I think we're just going to go ahead and begin. We ended yesterday on the colligative properties. And we had talked about Raoult's law, and we talked about osmotic pressure. And we even went through a couple of the problems of each. Now, just to go over Raoult's law, a question in the quiz. What you do is you are either given the normal vapor pressure, the vapor pressure of the pure solution, and asked to determine what the vapor pressure of a solution is, or you will be given the vapor pressure of the pure stuff and the solution and asked to determine something about the mole fraction. Raoult's law. The new pressure is equal to the mole fraction times the vapor pressure of the pure liquid. Remember, when you are doing this, you want the mole fraction of the solvent, not the solute, the solvent. Osmotic pressure. As soon as I find it, still boiling point. Maybe it's beyond this. Yes, it is beyond this. Osmotic pressure is going to be, osmotic pressure is related, has the symbol pi. Osmotic pressure is going to be equal to moles over volume, or the molarity, times R times T. So, did I do a problem in this Did I do a problem in this question?
I don't think so.
Okay, we'll go through it. We're going to go to the slideshow right now so you can see it. You got 125 milligrams of an alkaline earth metal chloride. It's dissolved in enough water to make 50 milliliters of solution at 298. It has an osmotic pressure of 1.16. Using Raoult's law, what can I solve for? I have Raoult's law being pressure is equal to the molarity times R times T. Do I have the temperature in that problem?
Yes.
298. Do I have a way to get the molarity of this problem?
Yes.
And do I have the osmotic pressure?
Yes.
Okay, so I can use the information I have in the problem to solve for the molarity, correct, guys? If I solve for the molarity, I also know how much solution. Can I then get moles?
Mm-hmm.
I have the milligrams of my sample and I have the moles. I've got grams and I've got moles. Can I get the molecular weight? All right, I can get the molecular weight. Then I know how much contribution the Cl2 has. Can I subtract that from the molecular weight to get the weight of what my X is? Okay, so that is the strategy we're going to use for this. So if I'm doing this problem, my osmotic pressure is equal to molarity divided by R times RT. So I'm going to take my pressure and divide it by RT. I'm going to take the 1.16 atmospheres divided by R divided by the temperature. I've got a molarity of 0.0474 moles per liter. Now, we're going to learn in a few minutes what Hoffman's law is. Hoffman's law says that since colligative properties are related to the number of particles and not the number of the molarity of the entire molecule, when I have XCl2, I have 3 particles that are being produced. So to get the molarity of the original XCl2, I have to, this M is the molarity of the particles. It's not the molarity of the XCl2. So I have to divide the 0.0474 by 3 to get the molarity of the XCl2. I then multiply by my liters, I get the number of moles. I've got my grams, I divide that by my moles. This gives me a molecular weight of 158 grams. Contribution from chlorine is 35.5 plus 35.5 or 71. So the molar mass of 158 minus 71 gives me a weight of 87 of my X. I look on the periodic chart and I find out that that element is strontium. Questions about that, ladies and gentlemen?
Question.
Yep.
And when you talk about particles and
Yes.
the number 3, I just want to make sure because I think I'm confused. I think I'm thinking of something else. But are you talking about I? Like.
Yes.
Okay.
Yes.
So can you explain a little more?
I'm going to go into that, and I'm going to go into that momentarily.
Okay. Cool.
Part of the problem in IA was I went directly into osmotic pressure. I normally teach, because of time constraints of Tuesday, I went directly to osmotic pressure. I wasn't anticipating having to teach you I. Does that make sense, Anaya? So it was a little bit out of place. All right, we're going to get into freezing point depression and boiling point elevation. All right, now, boiling point is kind of real easy to understand because part of the job of the solvent is to keep the solute dissolved. So there's an interaction between the solute and the solvent. If there is that interaction has to be greater than the solvent-solvent interaction. If it wasn't, then the solute wouldn't be dissolved. So we have a greater interaction between the solute and the solvent. So since we have greater intermolecular forces, it's going to take more energy to boil it away. So we get a boiling point elevation. Always, if you have something in a solvent, your boiling point will be higher than it is without the solvent. Is that making sense to you all? Thank you, Jennifer. Give me a thumbs up. Okay. Now, freezing point depression is a little harder to kind of wrap your mind around. All right. If the job of the solvent is to dissolve the solute, what I am doing when I am freezing the liquid, I'm taking it away from the solute in order to freeze it. So literally, it's happy where it is. In order to freeze it, I have to put more energy in to take it away from the solute. If I have to take more energy away to get it away from the solute. If that's the case, my freezing point temperature goes down. Freezing point goes down, boiling point goes up. Now, is there a temperature difference? Am I dealing with temperature here? I am dealing with temperature. And if I'm dealing with drastic temperature changes, my concentration would change if I used molarity. Therefore, I can't use molarity because molarity is based upon getting the volume of the solvent or the solution, getting the volume of the solution. That changes if the temperature changes because the density of the liquid changes. So I got to use another concentration term. The concentration term I use is molality. The change in the boiling point is proportional to the molality of the solution. So the temperature change is going to be equal to the constant times the molality. Understand that this temperature change is going to be a positive one because it is going to be boiling point elevation. Freezing point, same equation. Freezing point depression is going to be the freezing point constant times the molality. But now you have to understand that this change in temperature gets subtracted from the normal freezing point. I've already explained this. Note The temperature change doesn't depend on what the solute is, but how many particles are dissolved. So what is the freezing point? I can't read the question. What is the freezing point of a solution containing 478 grams of ethylene glycol, antifreeze, in 3,202 grams of water? The molar mass of ethylene glycol is 62.1, and the freezing point constant of water is 1.86 degrees centigrade per molality. Parker, how am I going to do this question? Parker, I can't hear you. You need to unmute, Parker.
Oh, can you hear me now?
I can hear you now.
Okay. So first you would have to find the how many moles you had of the antifreeze.
How are you going to do that?
By multiplying the molar mass. I mean, not multiplying. You divide molar mass by the grams.
Okay. So I've got the mole. I do that. I get the moles of ethylene glycol.
And then you would multiply that by the constant for the water.
That gives me moles. Is that what I want? The formula for freezing point depression is...
Oh, it's molality. Hold on. I do not know the formula for molality.
Molality?
Yeah.
Anybody out there know it?
The formula for molality is grams of solute over molar mass of solute over kg solvent.
Okay, is that Anaya?
Yeah.
Okay. What Anaya said was the molality is equal to the moles of the ethylene glycol divided by the kilograms of water. So I do that out. 478 divided by 62.01 gives me 7.85 moles. I simply divide that by 3.202 kilograms. I get a molality solution of 2.41 molal. Then all I got to do is multiply that by the constant, and that gives me a minus 4.48 degrees Celsius. I have to subtract that from 0 degrees to tell you what the new freezing point is. Questions on it?
So for freezing point, we always need to subtract from 0?
Yes. Not, well, wait, time out. If it's water, the answer to that is yes. If it's something else, you have to subtract it from the freezing point of what that something else is.
Perfect.
Okay?
Can I just clarify something real quick?
Yep.
The 3.202 kilograms of the solvent, that came from the 3,202 grams of water, right?
Correct.
Okay.
I just converted it. I'm hoping that you guys can see that the 3,202 grams of water is equal to 3.202 kilograms.
Okay.
Any other questions, guys?
Yeah, what was the answer?
Negative 4.48.
All right, thanks.
All right, let's look at this question. What should depress the freezing point of water more? 100 grams of ethanol or 100 grams of CH4O? Methanol. Ethanol or methanol?
Probably ethanol.
Which weighs more? Come on,
But
you can just look at
ethanol
this.
weighs more.
C2H6O or CH4O. Which one's going to weigh more molecular, have a greater molecular weight?
Ethanol.
So in order to get moles, are you dividing by the molecular weight?
Oh, wait.
No?
Oh,
To go from grams
Yes.
to moles, are
Yeah,
you
yeah.
not
Mhm.
dividing by the molecular weight?
you divide by the molecular.
So if you have the same amount of grams of both compounds and one has a higher molecular weight than the other, which one is going to have more moles?
Oh, okay, the one with less.
The one with the smaller molecular weight. So I have more moles of methanol than I do ethanol. Molality is moles over kilograms. So I have a higher molality for the methanol than I do of the ethanol. If I have a higher molality, this leads to a higher freezing point depression. Again, guys, logically work through these problems. Now, again, we're talking about the colligative properties that are dependent on particles. If I have an electrolyte or an ionic compound, that's going to break up into more particles because it breaks up into its ionic form. If I have sodium chloride, I should get twice as many particles with sodium chloride as I do with something like methanol that doesn't break up. So the same concentration of sodium chloride and methanol, which one will lower freezing point more?
Methanol.
Okay. Again, colligative properties are based on number of particles. When I have an ionic compound and put it into water, that splits into its ions. Ions are particles. So I start with one NaCl, I end up with Na and Cl, 2 particles. Methanol does not break into.
Okay.
So, as you just said, since salt breaks into 2 particles, if I have the same concentration of salt and methanol, methanol does not, the salt will lower the freezing point more.
Okay.
It's not exactly 2 particles. Not exactly. Because some of the salt stays together as sodium chloride. It's not 100% dissociation. Some of the sodium chlorides will stay together as sodium chloride and be entirely surrounded by salt. So ideally, the number for sodium chloride is 2. Realistically, it's a little bit less than that. If you have a higher concentration, you are more than likely going to have reassociation. Therefore, the Hoffman factor changes with concentrations. If I'm looking at something like sodium chloride, at 0.1 molality, you get a Hoffman factor of 1.87. Oh, this is number of particles. Okay. So as you increase the concentration, the number of particles is going to decrease. We have to modify our previous equation a little bit so that our freezing point depression is still equal to the freezing point of water times the molality. Now I have to shove in the Van Hoff factor, which is the number of particles that are produced. What elevates the boiling point of water more? 10 grams of sodium chloride or 10 grams of magnesium chloride?
Magnesium chloride.
Okay, sodium chloride weighs about 58. Magnesium chloride weighs about 95. So we are going to have, I'll say roughly speaking, about half the number of moles of magnesium chloride as we do sodium chloride. Does that make sense, guys? If I have half the concentration of magnesium chloride than sodium chloride, but I'm taking that half concentration and I'm multiplying it by 3. I'm taking the sodium chloride and multiplying it by 2.
Why?
So ultimately, the weight factor of the sodium chloride overcomes the magnesium chloride. So sodium chloride should elevate it more.
Why? Why multiply by 3 and 2? Is that the particles?
That's the particles. Sodium chloride breaks up into 1 sodium and 1 chlorine. Magnesium chloride breaks up into 1 magnesium and 2 chlorines. So there are 3 particles here, 2 here.
Question.
Yeah,
so
Anaya.
those are obviously ionic bonds because they dissociate in water. So when they dissociate, you're counting the particles individually. So like magnesium would be 1 and chlorine would be 2 because of the amount of chlorines there are.
The subscript for the chlorines in there, yes.
Okay, cool. Yeah, that makes sense.
Okay.
Does that also have to do with intermolecular forces?
No, this has to do more with, well, okay. I answered that before thinking. Yes, yes, it does. Because you have more of the particles, you have to surround them with more water molecules, right? Mm-hmm. You have to commit more water molecules to the dissolution. If you have to commit more water molecules, there's more intermolecular forces, which makes you raise the boiling point that much higher.
So sodium chloride would have the highest intermolecular force.
Well, again, we got to talk about the total number of particles. Let's do the math out here, guys. Might as well do the math. 10 divided by 58 equals the moles, right? I got 0.172 moles of NaCl, or 0.344 moles okay. 10 grams divided by the molecular weight gives me the moles of NaCl. So that's 0.172 moles of NaCl. But since it breaks up into Na plus and Cl minus, I get twice as many particles of the ionized solution. On the other hand, I have 10 grams of magnesium chloride divided by the molecular weight of 95. I get, this is my moles of MgCl2. That is equal to 0.105 moles. Or 0.315 moles Mg 2 plus Cl minus plus Cl minus. Are you seeing where I got these numbers from?
Yes.
Okay, so in actuality, the 10 grams of NaCl makes more moles of particles than the 10 grams of MgCl2. Looking at it, I thought it was pretty much a crapshoot to begin with. Questions, ladies and gentlemen? That's pretty much the end of this particular chapter. Any questions on colligative properties and solutions? Are we seeing the slideshow, ladies and gentlemen?
Yes.
Thank you very much, Jordan. So what we're going to talk about, we're going to talk about reaction rates. We're going to talk about how we measure rates. We're going to talk about rate laws, what the rate depends on. We're going to talk about integrated rate laws, how to relate concentrations to time, half-life, how long it takes to react 50% of the reactants. We're going to deal with how the rate constant changes with temperature, and we're going to deal with mechanisms. I'm hoping to get all the way through to the integrated rate law today. I'm hoping next Tuesday we get through Arrhenius's equation, and by next Thursday we get through mechanisms, because the Tuesday after that we have a test. I believe that is June 8th. So what kinetics is going to examine is it's going to examine reaction rates. And a reaction rate is nothing more than concentration changes over given time frames. It's also going to examine how the reactions occur. Now, it's hard enough getting two molecules to bang together. Getting three is nearly impossible. So when we have highly complex reactions, they occur in individual simple steps. And we're going to learn about that. So reaction rates are nothing more than how fast the reaction occurs. It's dependent on three things: concentration of the reactants, temperature at which you have the reaction, and the presence of catalysts. Now, why do you think concentration affects it?
Because just the more particles are concentrated, the more particles will like bump into each other.
Exactly. Think about it now. You're going into a COVID classroom right now. Everybody's spread out. They're spread out because we don't want you bumping into one another. In a normal classroom, you're squeezed together in probably the smallest classroom they can fit you in. There's more chances you're going to bump into each other. If you have diseases, there's more chance you're going to spread them then. Same thing with chemicals. The more concentrated, the more chance they are going to bump into one another. They have to bump into one another in order to react. Now, what about temperature?
If you increase the temperature, it's gonna increase the kinetic energy in the particles, so they'll bump into each other more.
Okay, just the fact of two chemicals bumping into each other doesn't mean they're going to react. They have to bump into each other with enough energy to break bonds. So if I increase the temperature, the chances are I'm increasing the energy. That means that I'm going to get the reaction to occur. Catalysts aren't as obvious. Okay. Parker, you're going to Pittsburgh from here. It's almost a straight north shot, right, Parker?
Yeah.
All right. But you decide that on the way you want to see New Orleans, you want to pop up to Memphis, then maybe work your way over. The Kentucky Derby's happening, Louisville. And then you want to get to Cincinnati over and Columbus and to Pittsburgh, right? You went the long way, right?
Mm-hmm.
What happens if you had a super highway that went directly from Tampa to Pittsburgh, straight shot? Which one do you think you would get there faster?
If you just had a straight shot there.
That's what catalysts do. Catalysts affect the way that the compound gets made. It facilitates the combination of the compounds. Has anybody had biology? Have you had biochemistry and learned how proteins are made? What happens? Have anybody heard of RNA?
Yeah.
What happens with RNA is you have specific RNAs out there that latch on to amino acids in a very specific pattern. They latch on to one amino acid, then they get another one. You get two amino acids close to one another, you get a reaction between those amino acids. And it continues on, this chain goes on. So the RNA acts as a catalyst. Eventually, the entire protein molecule gets made and it gets cleaved away from the RNA to go react with more amino acids. Catalysts make a different path for the reaction to occur, but they get regenerated. Now, if I'm looking at a reaction rate, I can either monitor the amount of reactants depleting or the products increasing. I can monitor it that way either way. As I go on from time, if I all start off with red particles, after a little time, I get about half of them. Then after a little more time, I now have more blue particles than red ones. And what I'm going to do is I'm going to monitor the concentration of one versus the other. If I'm monitoring A, I've gone from 1.00 moles down to 0.30 moles. I'm decreasing A. If I monitor B, I'm increasing the concentration of B. Either way, I'm timing it. I'm finding out how much I'm depleting or how much I'm creating. So rate is nothing more than the change of concentration over the change of time. Note, if I'm dealing with reactants, isn't the change in concentration going to be a negative number? I start off with more. That's my initial concentration. My final concentration is going to be smaller. So when I subtract final minus initial, isn't that going to be a negative number? So if I'm looking at rates, the change of the reactants is a negative sign, but rate is always positive. So if I'm relating the rate of a reaction of the reactants versus products, I have to put a negative sign in front of this if I'm looking at reactants. Did that make sense to you guys? If I'm looking at reactants depleting, the rate is going to be negative change of concentration over change of time. If I'm looking at the rate of the products, the rate is equal to the positive change of concentration over change in time. So I have a reaction of butyl chloride making butanol. What I'm doing is I am monitoring my concentration of my butyl chloride over time. So if I do change a reactant over change of time, and I choose the first two, I do, since I'm looking at a reactant, this is negative 0.0905 minus 0.100. That gives me a number of negative 0.0095. I divide that by 50. I end up with a reaction rate of negative 1.9 e to the fourth, negative fourth. Note that this reaction rate is in concentration per seconds. That's the label of it. Questions on how I got this reaction rate? Now, as more time proceeds, the reaction slows down. Can anybody think why?
Because you have less particles forming.
Is that Ethan? Or Parker?
Manual.
Manual, sorry, Manual. That makes perfect sense to me. Remember we said rates are related to concentration? I'm using up my butyl chloride. If I'm using up my butyl chloride, the concentration's going down. If the concentration goes down, then the rate slows down. If I look at this, these rates between the steps, the rate is going down. The rate is decreasing as the reaction proceeds because I have less and less concentrated butyl chloride. If I had to plot that, I would end up with a hyperbolic curve. Now, what we are doing is we are taking the tangent of that curve to get the instantaneous rate at any time. So in effect, we're using calculus to determine those rates. Anybody doing calculus now?
Yeah.
Oh, good for you. Calculus is easy. Compared to trigonometry, it's very, very easy. So basically, we're using calculus to do these calculations. Now, if I'm going to relate the disappearance of butyl chloride to the appearance of butanol, the stoichiometry is 1-to-1, right? So the rate is going to be negative change in butyl chloride over time. That's going to be equal to positive change of butanol over time. Make sense? What if this reaction rate is not 1:1? What if the ratio is not 1:1? Say we're trying to equate the disappearance of H2 versus the appearance of HI. Wouldn't you agree that I get twice as many HIs for every loss of one H?
Yeah.
Okay. So I'm going to have to half the reaction rate of the HI to get it equal to the H2, because I'm making the rate for production of HI is twice that of what the rate of H2 is. So in order to make them equal, I got to multiply the HI rate by a half. Again, am I losing you? Are you understanding what I'm saying here?
Can you repeat it like one more time, please?
No problem. Okay, so who's asking the question?
I just asked if you could repeat it. This is Jordan.
Okay, Jordan. All right. Jordan, do you see for every H that I destroy, can you see I'm making 2 HIs?
Yes.
So I'm using one of these to make 2 of these. Now remember, I'm tracking change of concentration. So I'm making 2 of these for every one of these I'm using up. So the rate of HI is going to be twice that of H2. Jordan, did you understand what I just said?
Yeah, my screen just froze.
No problem. So if I'm making twice as many HIs as I'm depleting H2s, then in order to equate the 2 rates, I have to first put a negative in front of the H2 because it's a reactant and it's getting depleted. And then I have to put a half in front of the HI because I'm using twice as many HIs. I'm making twice as many HIs as I'm depleting of H2s. So to generalize, if I'm looking at reaction rates, if I'm getting reactants, I'm multiplying by a -1 over the coefficient. So the reaction rate of depletion of A is -1 over A times the concentration difference of A over T. That's going to be equal to -1 over B of the loss of B per time, which is equal to +1 over C, since C is a product, which is then equal to 1 over D. All I'm doing, whatever coefficient is there, in order to equate it with the other reactant or product, I'm equating it by taking 1 over the coefficient times that rate. Anybody confused? Let me see everybody's face. Thank you very much, Manuel. Zachary, where are you? Zachary, sorry.
I'm here, Professor.
Sorry, I got you. Your screen was, you were just pointing your screen up above it.
Right here.
All right. Okay, are we good with determining rates? Okay, now each reaction is going to have its own equation, and that's going to relate the rate to the reactant concentrations. It is called a rate law. Now, in order for a rate law to be valid, temperature has to be constant. If I change the temperatures, all bets are off. I have to say Temperature stays the same, no catalyst. Because reaction rates are dependent upon concentrations, temperature, and catalyst. Right now, we're trying to relate the rate to the concentration. If we're doing that, trying to make that one-to-one connection, temperature has to stay constant, and I can't involve a catalyst. Okay, I have my reaction going. Hydrogen plus iodine making 2 hydroiodic acids. If this is in 3 liters of solution, if the rate is negative 2.0 e to the minus 3, how many moles of HI are present after 400 minutes? Assume there's no HI initially and assume that the rate does not change. Anybody have an answer? Is the rate of a reactant depletion, or is it of the production of HI?
Would it be the depletion of the reactants?
How'd you know that?
Because it says the rate. Wait.
There's 2 reasons why you know it.
Is it because of the negative?
The negative sign is one thing. Negative means that we're talking about depletion. What's the other reason?
Because it says after 400 minutes.
The other reason is there's no HI. Okay, never mind. All right, so in order to relate, and we want HI. So we're going to have to change this reaction rate, which is of either H2 or I2 depletion. We have to change that into production of HI. How do I do that? What is the reaction rate? If the depletion of H2 is negative 2 e to the minus 3rd molar per minute, what is the rate of the production of HI?
Wouldn't it be that but positive and divided by 2?
Exactly. So the rate of I is 1 e to the minus 3rd molar per minute. Okay? Strategically, Natalie, if I've got a rate of 1 e to the minus 3rd molar per minute, look at the problem. Can you tell me what the concentration is going to be after 400 minutes?
You called me, right, Professor?
Yes, I called on you, Natalie.
Mm.
If the reaction rate is 1 e to the minus 3rd molarity per minute, that means each minute I'm producing 1 molar, 1 times 10 to the minus 3rd molar HI per minute. If I let the reaction go for 400 minutes, what's the concentration of my solution then? I don't know is a perfectly good answer, Natalie.
I don't know.
Perfect, absolutely. Natalia, can you lend something?
I don't know either.
All right, guys, think dimensional analysis. Jennifer, where are you? Jennifer.
I'm here.
Okay, where's here? I'm not seeing you in the screen, Jennifer.
Because I'm pushed back in order to see my screen and like type the notes. So the camera, but I'm here.
All right. Jennifer, do you know if I have a rate of 1 e to the minus 3rd molar per minute and I let the reaction go for 400 minutes, do you know what the concentration is after 400 minutes?
So would you use the equation and do the 1.0 e to the negative divided by 400?
Not divided.
Would you multiply them? If you're
Because I've got molarity per minute. If I multiply it by the amount of minutes, that's going to give me the concentration, right?
Yeah.
So I've got my 1 e to the minus third molar per minute times my 400 minutes. This gives me a 4 molar solution. The whole volume is 3 liters. I just multiply then the 4 times 3 liters. I have 1.2 moles of HI that's produced. Questions on it, guys? Sometimes the answers are simpler than you think they are. This is all just a dimensional analysis problem. I have molarity per minute. I just multiply by the minutes. That gets me the molarity. Molarity is moles per liter. I just multiply that by the amount of liters. Okay, to determine when we're dealing with the rate law, what we're doing is we're measuring the rate at different starting concentrations. So if I'm looking at my experiment, notice at some points I'm keeping one of my reactants constant, changing the other, and other points I'm keeping the other reactant constant and changing the first reactant. The reason I'm doing that is I'm trying to judge what the effect of concentration of this. If I change both of them, I don't know whether the rate has been increased by this one or this one. So what I have to do is I have to keep one constant while changing the other. Let's see who I got. Raylina, do you see the chart? Okay. Do you see an instance where the NH4 is, the concentration is doubling and the NO2 concentration is staying the same? Are you seeing that? Which experiment numbers are you looking at?
The first and second one.
First and second one. Okay. I have effectively doubled the concentration of the ammonia, right? What happened to the reaction rate?
It doubled as well.
It doubled. So is my rate dependent on the concentration of NH4? You doubled the concentration, you doubled the rate. So is the rate dependent on the concentration of NH4?
Yes.
Okay. Let's go to Leonardo. Leonardo, you there?
Yeah, I'm here.
Okay. Do you see an instance where the concentration of the NH4 plus is staying the same, but I'm doubling the NO2 concentration?
Yeah.
Which experiment numbers?
Would be between 5 and 6.
Okay, so I've kept the NH4 constant, but I've doubled the NO2. What happened to the reaction rate?
It doubled.
It also doubled. So is the reaction rate dependent on the NO2 concentration?
Yes.
Yes. So I've got my rate law being my rate is proportional to my NH4 concentration times my NO2 concentration. I change the proportionality into an equal sign by adding a constant. This equation is called the rate law. When I relate the rate to the concentration of my reactants, that is called a rate law. the individual parts of a rate law is the rate is equal to the rate constant times the NH4 raised to a power times the NO2 raised to another power. Since there's nothing written up here, assume they're 1. So we're determining the relationship between the rate and the concentrations at constant temperature. If I'm dealing with gases, instead of concentrations, I can use pressures because a pressure is kind of a concentration. K is a constant that has a specific value for each reaction. K is dependent on temperature. If we change the temperature, we change the value of K, which is why we have to keep the temperatures constant. We're going to get into that a little later on when we deal with Arrhenius' equation and temperature changes. Again, for a rate law to be valid, the temperature must remain constant. So when we're dealing with rate laws, the exponents tell the order of the reaction with respect to each reactant. So this reaction is first order with respect to the concentration of NH4 plus, and first order in terms of the concentration of the NO2. Guys, this is an abbreviation. We're going to be using this a lot in the next 4 chapters. If you have a symbol, a chemical symbol that is enclosed in brackets, that means that that is the concentration of that particular entity. So my reaction is first order in relationship to NH4 concentration and first order in relationship to NO2 concentration. But the overall reaction order can be found by adding the exponents of the reactions in the rate law. Overall, this reaction is second order. Now, this is always dangerous when I do this. Okay? It's always dangerous when I ad lib. No, I don't want that. I want home, new slide. Okay, experiment. Okay. Now, Jessica. Oh God, he called on me. Okay. Look at experiments 1 and 2, Jessica, and unmute. You're unmuted, Jessica? No, you're not. I'm not hearing you, Jessica. I'll come back to you, Jessica. Okay. Athar. Oh,
Yes.
you just happen to be on my screen, one up from Jessica. Can you talk, Athar?
Yes.
Okay. Look at experiments 1 and 2. Okay.
Yes.
I doubled the concentration. What happened to the rate?
Decreasing.
I doubled the concentration. What happened to the rate?
Oh, increasing, yes.
It increased by how much?
5.
Okay, but compared to the 10, what is 10 compared to 5? Is it twice as much?
Yes.
Okay, so I have doubled the concentration. I've doubled the rate.
Mm-hmm.
Does that make sense to you?
Yes.
Okay, so that means it's a direct relationship, right? Rate increased at the same time, at the same amount that the concentration increased. It's a one-to-one relationship, right? Ethan, you were there.
Yeah.
Okay. Look at 1 and 3. What happened to, what's going on here?
Okay, so with 1 and 3, the concentration of A is staying the same. The concentration of B is doubling. And
so what
the
happened to the rate?
overall rate is being multiplied by 5.
Or
exponentially. It's exponential. Yeah, it's like, yeah.
Did I square it?
Being squared.
Okay, I doubled the concentration. My rate went up by squaring. So in effect, what is happening is the relationship for B, it's not a direct relationship, but the rate is equal to B squared. Do you understand? Does everybody understand what I just went through? Jessica, shake your head if you understand. Give me a hands up. All right, thank you. I'm going to go through with that. See if everybody understood. Jordan, Jana, Parker. Samantha, stop laughing. Because I know it's not me. I didn't make a joke. Are we good, Leonardo? Everybody understanding what I just went through? Anaya, Benita? B doubled, the concentration doubled, but the rate went up by squaring it. So that the exponential relationship between B and the rate is that the rate is equal to B squared. Now, how do you determine this? Now, remember, guys, when I said in the orientation that intro was like stepping out the front door, Chem 1 is like jumping off the roof of your house. Chem 2 is like jumping off of a 5-story building. This is where that comes because we have to learn to manipulate equations to get our answers. How do we determine the order? We need to compare the reaction rates of different concentrations of reagents. I need to change one of the reagents while keeping all of the others the same. This is going to give me the relationship between the concentration of the first reagent and the rate. Then I need to change the concentration of the second reagent while keeping all the other reagents the same. If I've got a third reagent, I got to keep that the same while keeping the first 2 reaction concentrations the same. Then what I'm going to do is I'm going to divide the reagent equations with one another. And we're going to show you how that's going to happen right now. Just overall, that's the strategy we're using. We're going to see it now in place. I've got two reactants, mercuric chloride, mercuric 2 chloride, and oxalate. I do my first experiment. My concentration of HgCl2 stays the same. I'm changing the oxalate. Remember, I keep one reagent concentration the same. I change the other. And I look what happens to the initial rates. Now, my rate of 2 is going to be equal to my rate constant times my concentration of HgCl2 raised to the m, my oxalate raised to the n. I'm going to divide that whole reaction rate law by rate 3, which is equal to my rate constant times my concentration of HgCl raised to the m times my oxalate of trial of experiment 3 raised to the n. Now, if I keep the concentrations the same, did we change the temperature? Temperature has to be constant in these, remember that? If we kept the temperature the same, then my K is going to go away. If I keep the concentration of my one reagent the same, that concentration raised to any power over that same concentration raised to any power, does that cancel out? Try the numbers. Say you have a 2 molar raised to the 3rd power over a 2 molar raised to the 3rd power. 2 times 2 times 2 is 8. So I got 8 over 8. They cancel out. Try any other number. Give me a number, Benita.
5.
5? 5 raised to how many powers? Don't go beyond 4.
2.
5 raised to the 2nd power is 25. Over 5 raised to the 2nd power is 25. Do you understand? As long as I keep the concentrations of my oxalate the same, they're going to cancel out. So originally, I didn't know what the value of K was. I didn't know what the value of M was. And I didn't know what the value of N was. I had 3 variables. If I divide one rate law by another and keep the concentrations of one of my reagents the same, it cancels out. Because I'm dividing K by K and I haven't changed the temperature. The Ks are the same, they drop out. So now I have a new equation with only one variable. So I take 7.20 times 10 to the minus 5th divided by 3.6 times 10 to the minus 5th is equal to the concentration of my HgCl2 of my 1 trial, which is 0.105 raised to the m, divided by 0.0520 raised to the m. Now, 0.105 raised to the m divided by 0.0520 raised to the m is the same thing as taking 0.105 divided by 0.0520 and raising that to the m. That's a mathematical translation. So I have 2 is equal to 2.02 raised to the m power. If I want to do the math out, the legitimate math, I would do, let's see, layout. To solve this legitimately mathematically, I have to take the log of both sides. So I got the log. The log of 2.00 is equal to m times the log of 2.01. The exponents always have to be a whole number. So in this case, just round that to 1. This is the actual math that's involved. This is how you go from this number to solving for what m is.
I have a question.
Or 1 second.
Okay.
Or I can just look. I can just look and think 2 is equal to 2.02 raised to 1 power. It's 1. You get the same number back if you raise something to the first power. Somebody had a question.
Yeah, that's what I was gonna ask. I was just gonna ask.
Is this Anaya?
Yes. If I could just ask myself what you just said. So that's what I was double checking on. And
yes,
for M, that's in respects to HGCL.
Right here.
Okay.
Says it right here.
Oh, I was just making sure that that's how that was done. Okay.
That's with respect to the HgCl2. Now, I know my rate law, I now know that my HgCl2 exponent is 1. So m is equal to 1. I have to go back to my original equation. All right, before we looked at keeping the oxalate numbers the same and changing the HgCl2. Now I want to keep the HgCl2 the same and change the oxalate. Can somebody give me an instance where that occurs? Which experiment numbers? HgCl2 concentration stays the same now. Oxalate changes.
1 and 2.
1 and 2 will work. Can somebody suggest another example?
3 and 4.
I can use either experiment 1, compare it to 2, or I can use experiment 3 and compare it to experiment 4. Remember, I'm keeping my HgCl2s the same, changing the oxalate. So when I do that, see where that's at. That's here. Okay, I'm comparing rate 2 over rate 1. Again, I'm writing my rate law for rate 2, K times HgCl2. I could have put 1 here because I've already solved for HgCl2. That's times the concentration of oxalate raised to the n. My rate 1 is equal to the rate at reaction 1 times the reaction constant times the concentration raised to the first power of HgCl2 times oxalate raised to the n. This time, instead of canceling out my oxalate, I'm canceling out my HgCl2. That reduces my equation to 7.20 times 10 to the fifth over 1.80 times 10 to the minus fifth is equal to 0.3 raised to the n over 0.150 raised to the n. This number reduces to 4. This reduces to 2 to the n. Now, 2 raised to what power is equal to 4?
2.
2. Or if you want to, you can do the actual math out. If you want to do the actual math, you can do the actual math. Now, I figured out that my exponent with relationship to my oxalate is 2. My exponent with relationship to mercuric chloride is 1. What is the overall order of my rate law?
Would it be the third order?
It's overall a third order. Okay? Now, we know what, let's go back to the original slide. Originally, we had K, M, and N that we were solving for. We now know what M is. We now know what N is. Can somebody suggest how we are going to solve for K?
Couldn't you just use the top half of the equation and then just solve for K?
Exactly. All I'm going to do is I'm going to substitute in the rate for my experiment 2. K, I don't know. I know that my concentration of mercuric chloride is 0.105 raised to the first power times my concentration of oxalate raised to the second power. I then solve for K that way. In this case, I chose rate 1. Question?
Sorry, the powers were determined by the order, right?
Yes.
Okay, cool.
Exactly. So I'm going to plug into my first equation to find K. My first rate was 1.80 times 10 to the minus fifth. My concentration of mercuric chloride was 0.105. Concentration of oxalate was 0.105. So all I'm doing is substituting in 0.105 raised to the first, 0.105 raised to the second is equal to my reaction rate. So my K is equal to 7.62, 10 to the third, molarity to the minus 2, minutes to the minus 1. Understand, the label for K is going to vary depending upon the exponents. Because this is molarity to the first times molarity to the second. I'm getting molarity to the third. I divide by this number. I take one of the molarities away. That's what gave me the molarity to the minus 2. Do we want to go through another one? Your choice.
Yes.
All right. I've got chloromethane plus 3 chlorines making carbon tetrachloride and 3 HCl's. I've got the concentration of my chloromethane and the concentration of my chloride. And I have the rates. So, Rhea,
yes.
We're just going to solve it the same way we did before. Again, I'm going to look for concentrations that are the same in one reagent and changes in the other reagent. So let's look at the trials here. Which line? I don't want to do that. Which line has one of the reagents staying the same and the other concentration changing? Rhea.
1 and 2.
1 and 2. What's staying the same?
The Cl2.
The Cl2 staying the same. Chloromethane's changing. So what I'm going to do is I'm going to set up a rate law for the first line divided by the rate law for the second one. My rate for the first, did I do first over second? Yes, I did first over second. Rate on my first line is 0.014 molarity per second. That's equal to K times the concentration of my chloromethane, 0.50 raised to the M, times my concentration of the chlorine raised to the N. That's equal to, or that's divided by my rate of my second experiment, in which my chloromethane changed concentrations, but my chlorine stayed the same. So I got 0.029 molarity per second is equal to K times 0.1 raised to the M times 0.5050 M raised to the N. Rhea, I'm sorry, Rhea, what is going to cancel out?
The 0.050.
This is going to cancel out. This is going to cancel out. What else, Rhea?
The K.
K's are the same. I haven't changed the temperature, so K's are the same. They drop out. So this whole thing then simplifies to 0.014 over 0.029. That's equal to 0.5 M over 0.1 M raised to the M power, which is like saying 0.5 raised to the M power. So I got 0.48 is equal to 0.5 to the M. What do you think M is?
1.
1. Or else if you want to do the math out, the log of 0.48 is equal to M times the log of 0.5. 1 is going to be M. Now, Gianna, we're going to do the same thing for chloride. Only in this instance, we're keeping the concentration of my chloromethane the same. Which lines are we dealing with now?
You said we're keeping the chloromethane the same?
We've already done the chlorine. We've already done the chlorine, so we're going to do the chloromethane next.
So the third line or the third section?
Which one? This one or this one?
Yes. The one above that, yes.
This one? And
No,
what's the
no,
next
you were
one?
just on it, the third one.
This one?
Yes.
Okay. Which other one are we going to do?
And then the second one. So the second one and the third one.
Second one and the third one. And I'm going to make this. My rate is equal to my chloromethane raised to the M times my chlorine raised to the 1, because we just determined that, times K. So in this instance, I get 0.029 is equal to K times 0.100 raised to the first times 0.050 raised to the n divided by 0.166 is equal to K times 0.100 raised to the first times 0.100 raised to the n. Once again, the K's and the 0.100s drop out. That reduces to 0.029 over 0.166 is equal to 0.05 over 0.1 raised to the n. I got 0.25 is equal to 0.5 raised to the n. Or the log of 0.25, which is negative 0.602, is equal to n times 0.301. Therefore, n is equal to 2. To get K, I simply use, again, one of my rates, and I make the rate equal to K times, plug in the concentration, plug in the order of that, plug in the concentration, the order, then I solve the algebraic equation. Questions about this? How much time have I spent on this, Jenna? Have I spent a lot of time on this particular equation?
Yes, you did. That means
okay.
it's
What are the chances? Guys, one of the things you should always ask yourself as the professor is talking through things. Is he spending a lot of time on this? Is it highly likely he thinks it's important? Therefore, is it going to be on the test? Okay, we're at 11:43. Do you guys need a break? Okay, 5 minutes. I need a break. I need coffee. Okay. Okay, guys, I'm back. Athar, I saw. Jordan, I saw. Vanessa.
I'm here.
Thank you, Vanessa. Natalia, I saw. Danny, I got a message, is not here. Is that correct? Benita, I saw. Sarah, I saw. Gianna, I saw. Jenna, I saw. Jennifer, I saw. Manuel, I saw. Parker, I saw. Samantha, I did. Shari. Is Shari here? Araceli.
I'm here.
Thank you. Jessica. Is Nicole Capas here? Nicole Capas. Alexander McKinnon. Keanu, is Keanu here? Keanu. Valeria.
Here.
Jana.
Here.
Jenna.
Here.
Leonardo, I saw. Anaya, I saw. Natalie, I saw. Sachari. Are you here, Sachari? You've been in and out.
Yes. No, I've been here the whole time.
Okay. Relina. Relina.
Yes, I'm here.
Ria is here. Emily, I saw. Galexis. And Ethan.
Here.
I gotcha. Okay. Any questions on what we just went through?
Excuse me, Professor. I'm not sure if you called my name. I had to step away for a little bit.
Who's that?
Gianna.
I got you, Gianna.
Okay, thank you.
What about me, Sarah?
Sarah?
Mm-hmm.
I got you.
Okay, thank you.
Some people I kind of saw and I saw on the screen and kind of marked you down. Okay, any questions about what we went through? What that problem is like is the old algebra problems when you had two variables and you had to kind of solve them. So you basically had to kind of subtract one equation from the other to eliminate one of the variables so that you can relate it at a later time. Do you kind of remember what I'm talking about? That's a very important question. Now, in the next 30 minutes, I'm going to try and get as much of the integrated rate law talked about as possible. Now, it's important what we've done. The rate laws are important relating rates to concentrations. That's important, but we also need to relate it to time. And the way we are going to need to do this is we're going to need to integrate it, and we're going to need to use calculus. So we are only going to deal with zero order, first order, or second order. Those are the only three possibilities we're going to really deal with. Because if getting one thing to explode or getting two things, the rare chance of getting two objects bumping into each other, that is extremely rare. To get a position where you get three things bumping into each other at the same time, that's astronomically rare. So what we're going to do with our rates is we are going to integrate them. And when we integrate them, we are going to develop a formula, y is equal to mx plus b, a straight line. So we're going to try and integrate them in such a fashion to make the formula of a straight line. And then we're going to see what we need to plot to get that straight line. Each one of these orders, I'm going to have a different y and a different x. Let's consider first order. Now, if I've got a first order equation, my rate law is rate is equal to my rate constant times the concentration. First order, only one exponent up there. But my rate is also equal to negative delta A concentration divided by my change in temperature. So since the rate is equal to both of them, I can set this equal to that. Then, with some calculus magic, if you want to go through the derivation, it goes through all of this forms to end up with that equation. The concentration at some time is equal to the original concentration times E raised to the negative rate constant times the time. This is the derivation. This is the equation we end up with. And you're going to have, if you're not used to natural logs, you're going to have to get used to them throughout the rest of the semester. Now, I've got this in this form. I want to get to the equation of a straight line. I can do that if I take the log of this side, the ln of this side, and the ln of this side. I've got then the ln of the concentration at some time t is equal to the ln of the concentration at time 0. ln times e raised to the power goes away, and we get minus kt. I rearrange that to get, if I have ln of A0 on the right, this means negative ln, which means if it's negative ln, I can rewrite that as the ln of the concentration at time t over the original time. That's equal to kt. I can rearrange this back so that I get the ln of the concentration at some time t is equal to my rate constant times time plus the ln of the time at some time 0. This is in the equation. Y is equal to mx plus b. So in a first order process, if the reaction is first order, if I make a graph of the ln of the concentration at some time t versus time, I will get a straight line, and that straight line is equal to my rate constant. Bottom line. Bottom line, if I plot ln of the concentration at some time t versus my time, I get a straight line that proves it's a first order process, and the slope of that straight line is going to be negative k. Consider a process in which methyl isonitrile is converted to acetonitrile. How do I know this is a first order reaction? Okay, I plot the pressure. The pressure is the same thing as concentration. I plot the pressure versus time. I do not get a straight line. Not a straight line. I then plot the ln of the pressure versus time. I get a straight line. Because I got a straight line, it's a first order reaction. I find the equation of this line, and the equation of the line gives me a slope of 5.1 times 10 to the minus fifth. That is my constant, my rate constant. Are you with me yet? Are you with me? If I do the integration for a second order rate law, I get a rearrangement of 1 over the concentration at time t is equal to KT plus 1 over the original concentration. Again, I have a equation of a line, but this time, instead of plotting the ln of the concentration versus time, I'm going to be plotting 1 over the concentration versus time. That will give me a straight line. If that gives me a straight line, I have a second order rate law with the slope being a positive k. And if I plot 1 over ln, if I plot a graph, this axis is wrong. 1 over a versus time, I get a straight line. If I do a zero order, I integrate the equation, I get A at some time t is equal to minus KT plus the original concentration. So in this instance, I'm plotting the concentration at some time t versus time. If I do that, I get a straight line. Important slide. This is the slide that relates rate laws to the integrated rate law to the half-life. If I have a zero order, this means that the rate is equal to k times a raised to the 0 power. What is any number raised to the 0 power?
1.
So really, in a zero order, the rate is just equal to the rate constant. First order, the rate is equal to the constant times the concentration. Second order, rate is equal to constant times the concentration squared. Integrated rate law. Concentration is equal to minus KT plus the original concentration in a zero order. So I'm going to plot concentration versus time, and that will be a straight line. If I have a first order, I'm going to plot the ln of the concentration versus time. That will give me a straight line. If I have a second, I'm going to plot 1 over A is equal to KT plus 1 over the original concentration. So I'm going to plot 1 over A versus T. We'll get into half-lives a little later. So I've got the decomposition of NO2 at 300. It's described by this equation. It yields this data. So what I have to do is I have to take these concentrations, if I plot concentration directly versus time and get a straight line, it's zero order. I then have to take the ln of this. I have to go through and plug in ln of 0.01, ln of 0.00787, and so forth. If the plot of the ln versus time gives me a straight line, it's first order. I then have to make a third column 1 over the concentration. And if 1 over the concentration versus time gives me a straight line, that will be my order. So I plot ln of NO2 versus time. Do I get a straight line? Benita, is that a straight line to you?
No, it doesn't look straight.
Doesn't look straight. So therefore, my ln versus t did not give me a straight line. Is this a first order reaction?
No.
I'm going to make another column. In this case, I'm going to take 1 over the concentration and plot that versus time. Benita, did this give me a straight line?
Yeah, that's straight.
So I got a straight line. This means that by plotting 1 over the concentration versus time, I got a straight line. This means that it is second order in relationship to NO2. That would be a pain if I made you do graphs in a test, wouldn't it? Relina, wouldn't it be a pain? Leonardo, would you like to do that? Would you like me to make you hand graph something in the middle of a test?
Please, no.
There's a solution. There's a solution. Use the data points and determine whether the slope is changing. I have A versus time, ln of A versus time, and 1 over A versus time. All I need to do, these points are supposed to be on the straight line. If the slope, if I use 0 and 5 and 80 and 2.5 as my points on the line, if that slope equals 160 and 1.67 and the slope between that and 240 and 125, if the slopes are equal, then I've got a straight line. If the slopes are different, then I don't have a straight line. So what I'm going to do here, I'm going to check for zero order. Zero order means I'm plotting concentration versus time. And my first point was y value of 5, x value of 0. My second point was y value of 2.5, x of 80. I do the slope calculation. I get 0.0313. I'm going to choose another value. What I did was I took this one and this one, figured out the slope. Now I can use 0 again and compare it to the third one. Or I can compare, let me see what I did. I can compare the last two. Remember, my concentration is 1.25 at 240. It's 1 at 320. So I'm going to do the slope. 1 minus 1.25 over 320 minus 240. Did I get the same slope? Therefore, it is not zero order. For first order, I'm going to take the ln of my concentration and compare it to the time, plot it versus the time. So I'm going to take 0 and 1.61 and 80 and 0.916. I do that, I end up with my slope of 0.00868. Now I'm going to choose two other points. I'm going to choose this line. I'm going to use 0.223 and 240 and 0 and 1.61. Hold on a second. I don't know what I did there. Oh, I used 3 and 4 here. Sorry, I used 3 and 4. So I'm using 240 and 0.223 and using 320 and 0. So my 0 minus the 0.223 over 320 minus 0, that equals this. Do these slopes equal one another? It can't be first order. Now I'm going to plot 1 over A versus the time. And I'm going to use the first two and the last two. I get 0.400 minus 0.2 over 80 minus 0, 0.00250. My second one is 1 minus 0.2. 1 minus 0.2 divided by 320 minus 0. Do these slopes equal one another? Therefore, since I got the slopes equal to one another for plotting 1 over A versus time, the slopes are equal. Therefore, it is second order. Are you understanding how I solved the order problem? I have what you're going to get. This is what you're going to get in a test. You have to make 2 more columns out here. You have to take the ln of each one of these values, and you have to take 1 and divide it by each one of these values to make these 2 columns. Then you are going to take 2 of the points to find the slope. You're going to choose 2 of the other points to also get a slope. You're going to compare the slopes. If they equal one another, then what you did to get the slopes, that will be your answer as to zero order, first order, second order. Is there anybody confused at this point? Okay. So We've determined that it is second order. Now we've got the slope. We need to go back to determine K. We do that by looking at the important slide. We know that it is second order. So the rate constant is just equal to the slope, which is K. Okay, I'm sorry. Boom, 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 boom. Okay, 1 second. Let me try and get where I was before. All right, I think that's as good a place as any to stop for today. I'm going to create another problem of this ilk. And I will begin Tuesday's class with this. What I expect to get done, I expect to continue with half-lives. Then we are going to go into temperature, which involves something called Arrhenius's equation. That is what is happening next Tuesday. And then after that, we're going to get to mechanisms. And mechanisms, I'm looking to get the mechanisms on next Thursday. I won't be doing this the whole period. So there will be a little bit of chance for you to grab your questions and ask me. Does anybody have anything left? Anything they want to ask me?
I have a question.
I'm here, Anaya.
It's about the lab today.
Yep.
Do I have to wear one of those, buy a lab coat?
Yes.
Do they offer that at the Ybor or the Del Mabry campus?
Go to the bookstore.
Okay.
They're not that expensive, Anaya.
Okay, cool.
I'm sorry, somebody bought one.
They're like $5 at the bookstore, and
they're real cheap.
Yeah, they're $5.
It's like a plastic bag.
And the goggles, the same price.
Okay, so they are real cheap.
You can get a nice one for like $20 at Worker.
And then you stain it with chemicals and
yeah.
Okay. Anything else, guys? I will see you next Tuesday then. Some of you I will see in about an hour and a half.
Thank you.
Take care.
Thank you.
See you in class.
See you in class. Jessica, are you understanding this stuff?
Yeah. I wanted to tell you that I've got a flight next Tuesday, and I don't know if I'm going to be able to be here for half of the class. It's during it's between 11 and 2 o'clock in the afternoon. But I'll be able to make it for the morning.
What time is you're going
my
to be
flight?
able to, you're flying out?
I'm flying through Philly and coming back home. Yeah, on Tuesday.
I don't understand how you're going to be here in the morning, but
I won't, is what I'm telling you.
Okay.
Yeah, but thank you.
Jessica, just look at the Zoom meetings.
Okay.
And
it'll be recorded, right? In the cloud?
Hopefully.
Okay.
I always say hopefully.
Okay, all right. All right, thank you.
You're welcome.
Have a great day.
You have a great day too.